Okay. So now we have to decide the prediction. We have to predict whether the reaction would occur and not. So we have chosen the equations and then we put the values, the E naught values and the half equation. And we have to...
Sir, आपकी screen share नहीं हुई हुई.
Okay, sorry. Thank you. Yes, here we go. So the oxygen and hydrogen, this is positive 1.23 and this is positive 1.82. And whether the oxygen can oxidize cobalt to positive in acidic solution. So see, if it have to go backward, then this value must be higher than this one, right? If this value is higher, then this would go in a forward direction and this would go back in the backward direction, right? So, but this value is greater, so I can write over here, no oxygen cannot oxidize CO2 positive in acidic solution because the E value of cobalt 3 positive, 2 positive is or just greater than E naught of oxygen water. And you can mention the values over here that it's 1.82 volts, so it, and this is positive 1.23 volt. Is this understandable to everyone? Okay. Now, question number 7. The structure of a benzene 1,3 dicarboxylic acid is shown. Benzene 1,3 dicarboxylic acid. State the empirical formula of benzene 1,3 dicarboxylic acid. Okay, so for the empirical formula, if you look 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 carbons, hydrogen and oxygen. Oxygen are apparent that there are 4. Now hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So no, there is no hydrogen over here. So 1. Okay, 1 minute, sorry. It doesn't have a saturated, there are pi bonds. So 1 hydrogen over here, 1 over here, 1 over here, 1 over here, and 1 over here. Okay. So 4, 5, 6, 7. No, there is no hydrogen over here as well. So we have a 1 hydrogen over here, 2nd over here, 3rd over here, 3rd over here, 4th over here, 5th one, and 6th one. So C8H6O4. So if I would simplify it, it would be 4H3O2. So the empirical formula of this benzene 1,3 dicarboxylic acid is C4H3O2. Is this clear to everyone? Yes. If anyone have any confusion, do ask. Okay. In B part, benzene 1,3 dicarboxylic acid is an isomer of a benzene 1,4 dicarboxylic acid. These two isomers can be distinguished by carbon 13 NMR spectroscopy. Okay. State the number of peaks in the carbon 13 NMR spectroscopy of each of the compound. Okay. So, okay. Let me draw benzene 1,3 over here and benzene 1,4 over here. So, in benzene 1,3, we have a carboxylic acid over here and the other carboxylic acid over here on the third carbon, right? And here it's 1,4, so one carboxylic acid over here and one carboxylic acid over here. Is this clear? Okay, now have a look. If you look at this one, we can consider these two carbons exactly the same, right? Then this carbon is exactly in between these two C double bond O, so it have a different with these two. Then these two must be different because on one side they have a C bonded to C double bond O, and on the other side they have a CH2, and two carbons are these, which are completely different chemical environment, and now we are left with the one carbon. So C. Is this understandable? That we have how many now environments over here? 1, 2, 3, 4, 5. So it means that we will get a 5 signals of benzene 1,3 dicarboxylic acid. 5 signals. Is this clear? Yes. If you have any confusion, do ask. Now come.
Sir, 1,4 के 5 होंगे ना?
Hmm?
1,4 के
Sorry.
लिए 5 होंगे.
Why? It's 1,3. See, if you see over here, see this is if this is the first carbon, then it is the second and it is the third carbon, and then fourth, fifth, and sixth. So in this structure, I am getting 5 different environments. Because if you want to see over here, for example, on this carbon number 5, there are 2 hydrogens, right? On that carbon number 5, one of its neighbor is CH and the other neighbor is also CH, right? Now, so if you look at carbon number 5, it have a 2 hydrogens, first thing, and on both of its carbon are CH. But if you look at either carbon number 4 or carbon number 6, they both are bonded to one hydrogen, and one side they have a CH2 and the other side they have only one carbon. There is no hydrogen bonded to this carbon. So see, that's why 4 or 6 are similar but differ from 5 in a chemical environment. So in this way, if you see over here that in this structure where benzene 1,3 dicarboxylic acid, we have a 5 environments. If you have still any confusion, do ask. Yes. Yes, Soleh, is it clear?
Yes, sir.
Okay. Now have a look over here. Okay, let me do one more thing to make you understand. It's benzene 1,4 dicarboxylic acid. So see, let me draw the benzene.
सर एक सवाल है,
Yes.
आपको कैसे पता है कि आपने किस साइड से स्टार्ट किया काउंट करना? बिकॉज इसमें एक साइड से 3 नहीं होगा।
Yes. Okay. Let me recall you. That is the common rule in the IUPAC. Whenever we start assigning the number, we would prefer the side or where the side chain is the closer. That is the rule. So if I am putting this carbon number 1, so I can't do this 2, 3, 4 and 5, because when I do this, I am getting the chain on the third carbon. Did you understand?
Yes sir, thank you.
Okay, now have a look. We have this structure, and each of these carbon have a hydrogen, 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 and hydrogen. We are talking about carbon NMR. So whenever we are talking about carbon NMR, we would only observe the carbon atom and the environment around that carbon atom. And I'm still saying, if you have any difficulty or any confusion, do ask. Don't be quiet, just ask. Okay, now have a look. I can easily say that this carbon and this carbon have exactly same chemical environment, because both of the carbon have a one side a double bond O, the other side a single bond O, and on the other side a C, and that C is the part of the benzene ring. Is it understandable? Yes. So these two carbon which I highlighted with the red actually shows they have a same chemical environment, right? Is it clear or not?
Yes, sir.
Yes sir.
Okay. Now, if I mark this carbon and this carbon, aren't they have a same chemical environment? Because on one side of these two carbons, there is a carboxylic acid group, and the other two sides there are CH, right? So now, if you mark this carbon are different with the rest of the two. So, but if you see, there is a hydrogen on one side, there is a CH on the other side, and there is a CCOOH on the other side, right? So, if you mark this carbon also have a same environment. If you look at this carbon and this carbon, all these four carbon have a same environment C, because one side hydrogen, a hydrogen, a hydrogen, a hydrogen. Now, the other side, this C, C, and on the other side, they have a simply CH carbon, and the one remaining side have a COOH. So see, now how many environments I am getting over here? So how many signals I would get for benzene 1,4 dicarboxylic acid?
3.
Yes, 3 signals. Now, yes, is this understandable to everyone?
Yes, sir.
Okay. Now, next question. Benzene 1,3 dicarboxylic acid can be made by two-step synthesis shown below. Okay. And when we have a compound P, if you see a benzene having a carboxylic acid, so I can call it benzoic acid. And in step 1, it turns into CnC9C8O3. Okay, in step 2, Okay. Name compound P. So we know the name of the compound P, that it's a benzoic acid. Explain why the major product of this two-step synthesis is benzene 1,3 dicarboxylic acid, not benzene 1,4 dicarboxylic acid. Yes, can anybody recall?
S electron withdrawing, so they were more likely to be selling on 3 and 5.
Very good. There is a COOH group. Basically, direct the group to third position. Is this clear?
Sir, what?
Yes.
Sir, can you please explain?
Okay. I have shared the notes in the periodic over there. I will explain it, but for the time being, I will show you something. You can find these notes in the past paper WhatsApp group. Have a look over here. See, we have these things. Ahmed, can you mute yourself, please? Thank you. Okay. Now see, if the benzene ring have these groups bonded, and when we do the next substitution, then in this case, next substitution can occur on these positions. Okay, Alisa?
Okay, sir.
And when the benzene ring already have these groups, then the next substitution can occur on these two positions. Okay? Yes, is this clear to everyone?
Yes, sir.
Okay. So COOH group, it directs the group to the third position. Okay. The reagent used. Okay. So here we go. The reagents used for step 1 are CH3, COCl, and AlCl3. These reagents give rise to CH3C double bond O ions which react with the compound P. Okay. Name the mechanism of this reaction. So as we see that there is a substitution which occurred on a benzene ring, so we always call it electrophilic substitution. Okay, electrophilic substitution. Now draw the mechanism of the reaction of CH3C double bond O with a positive ion, so it's an electrophile. With a compound P, include all relevant curly arrows, charges, and the structure of the intermediate and the structure of the compound Q. Okay, so it's easy. See, remember that always the first arrow from the pi bond to this positively charged carbon, and another arrow from this double bond to this. No, sorry. That's it, because it was already positive charge. So this is the first arrow that we have to make. Now, Afterwards, we have a benzene ring.
सर
Yes.
सर ये हमने दूसरा एरो क्यों लगाया ऑक्सीजन वाला पॉजिटिव चार्ज से क्या मतलब हुआ
Can you repeat again?
सर ये पॉजिटिव चार्ज से क्या मतलब हुआ हमने वो दूसरा एरो क्यों लगाया उधर
Positive charge to beta, it shows that it is an electrophile.
सही सर
And we have to show the mechanism. So what happens during the reaction of a benzene with an electrophile? When the pi bonds from the benzene actually attacks the electrophile.
नहीं सर वो सही है मैं कह रहा हूँ ये हमने बाद में ऑक्सीजन वाला एरो क्यों हटाया हमने जो डबल बॉन्ड टूट रहा था
That actually happened. That doesn't happen over here. That happened in the addition when the carbon have already all the 4 bonds.
सही सर
And at that moment, when the nucleophile attacks on this carbon, then this bond is broken down.
सही ठीक है सर समझ गया ओके
But here in this case, it is actually like this, that there is a CH3 and C double bond O with a positive charge. So carbon have already one less bond. So there is no, this thing would happen over here. Okay.
सही सही सर
Okay. So here a carboxylic acid that is already bonded, and we have to keep that thing in mind that it's a carboxylic acid, so it is going to substitute the other group on the third carbon from it. So the third carbon would be this. So I would show C double bond O and CH3 over here, and a hydrogen over here, because this carbon or any of the other carbon of the benzene ring must have a hydrogen. And now here I would make a semicircle with a positive charge, showing that the pi system is still unstable. Now the hydrogen, you make a one curly arrow from this hydrogen to the benzene ring, and as a result, so the benzene pi system is also okay, it's a compound Q, yeah. So restore C double bond O, CH3, and here C double bond O, OH. Is this clear? Yes. Is it clear to everyone?
Yes, sir.
यस सर
Okay. Just give me a minute. Okay. Now, suggest a reagent and conditions to convert compound Q into benzene 1,3 dicarboxylic acid in step 2. Okay. So this is compound Q, and we have to convert this compound Q. This is compound Q, and we have to convert this compound Q into benzene 1,3 dicarboxylic acid, which means this thing. So how would we can do this? Yes, can anybody tell me how could we do this?
Sir, NaOH से करेंगे.
Just NaOH.
Iodine भी. Iodine और NaOH.
Okay. And any other reagent? We just do the oxidation with a magnet, or the other thing that you are telling, that this conversion can be done by 2 ways. Either one is we can use acidified
सर ये तो कीटोन है, तो कीटोन कैसे ऑक्सीडाइज होगा?
but that ketone is also bonded to a benzene ring.
तो फिर हो जाएगा?
हाँ, that is the possibility only because it is bonded to a high benzene ring. In the same way, alkane doesn't do an oxidation, but when the alkyl side is bonded to a benzene ring, it is oxidized, right?
है sir.
So that is the same thing. But the other thing is that is a methyl ketone, and for methyl ketone, when we use, the other reagent that can be iodine and sodium hydroxide. So what would happen in this, when we use this, we got this product, and the one that is CH3 removed from here would actually turns into CHI3 triiodoform. जी, यहाँ तक क्लियर है सबको?
सर यहाँ पे alkaline KMNO4 नहीं यूज होगा?
देखें, in either way, one more thing I have to mention over here, and then acidify. And the other thing, you are asking me the alkaline KMNO4, so I can do like this as well. Alkaline KMNO4, then acidify, and heat. Okay. Now the thing over here is, then when we use alkaline, we don't get carboxylic acid, we get its salt. In either way, whenever there is an alkaline medium, so instead of carboxylic acid salt is formed. So by the end, always have to put the acid to get restore the carboxylic acid from its salt. Is this clear?
Yes, sir.
Okay. Now question number 8. Alanine and glutamic acid are two naturally occurring amino acids. Okay. Alanine exists as two optical isomers. Draw the three-dimensional structure of these two optical isomers. Okay. So it's easy. Three-dimensional structure of so if you see, this is the carbon which is chiral, because on one side of it you have INH2, on the other side of it you have CH, the other side has CH3. So if I have to make the mirror image, Here it would come H. So these are the two optical isomers that you have to make. Okay, now proton spectrum. Okay, just give me a minute, please. Please just give me a minute. Okay, so we are provided with the proton NMR spectrum of either alanine in D2 or glutamic acid in D2O. Okay, state whether this spectrum is of alanine in D2 or spectrum of glutamic acid in D2. Explain your answer by reference to the number of peaks and split in pattern. Okay, so first make alanine and glutamic acid over here. So here we have alanine and here I'm going to make glutamic acid. Okay, so if I look at alanine, okay, here it is. So a C with a H, NH2, CO2H, and CH3. That is alanine. Now glutamic acid, a C with a H, NH2, CO2H, and then CH2, CH2, CO2H. Okay, these are the structures. And you have to explain your answer. Okay, so when I have put the D2O, what would happen? This hydrogen and these hydrogen would be replaced over here. And having a D deuterium, that same thing will happen over here. And we are having a D instead over at these places. So if you see afterwards, here, we have this hydrogen and these hydrogen with two different environments. But in this case, over here, we have this hydrogen, then we have this hydrogen, then we have these hydrogen. So here, three different environments right? Three different environments, which is indicating that I'm going to get three signals. And here, two different environments, so I'm going to get two signals. And if you see over here, the signals are two. So it means it's alanine okay, because just give me a minute, please. So we have to, it's of 3 marks, so we have to write 3 points, right? It's alanine because after D2O, two different hydrogen environments, but glutamic acid shows three different hydroproton environments. Is this point is clear to everyone? The other reason, if you see, here we are getting a quadrate, right? And it's a quadrate of this CH because in its neighbor there is a CH3. So this CH is showing you quadrate, but here there is no CH3 group over here. So we can say, or we can write alanine has a quadrate which cannot be shown by glutamic acid. And further, you can comment that if you see over here, the structure of the glutamate, okay, CH2, CH2, COOH. Okay, that's fine. So alanine has a quadrate. Because of one adjacent carbon is bonded to three carbons. Oh, sorry, three hydrogens, and that's why it shows a quadrate. Okay. And one more reason, if you want to, yes.
ऐसे ग्लूटामिक एसिड से हमारे पास कौन सी आ सकता है क्या लाइक जो ब्लू वाला है उससे आ सकते हैं
Yeah, there is another thing. See, let me tell you like this. For example, this one is going to show you a quartet, right?
Right.
And this is going to show you a doublet, right? Here you get a quartet, and for this you will get a doublet because adjacent carbon have a one hydrogen. Now, if you comes over here, here you will get a triplet, right? Because on its neighbor there is two hydrogens. And if you look over here to this one, you are again going to get a triplet, right? And for this one, yes, we can get a quartet. So that writing a quartet over here is not enough. We have to further write that and a doublet, and then a comment for a glutamic acid, that glutamic acid shows a quartet and two triplets. So that's how you will write. Okay. See over here, we are getting two triplets over here in glutamic acid. Is this clear now?
Yes, sir.
Okay. Now the next part, the mass spectrum of glutamic acid is obtained. State the ME value of the molecular ion peak. So it must be the MR. Can anybody calculate the MR and tell me what is the MR? G. Yes, can
Sir,
anybody tell me?
147.
147.
जी sir.
Okay. Now, the spectrum has a peak with ME values 88 and 131. Draw the structure of the ions responsible for these peaks. Okay, so we have to figure it out. These two structures having a MR of 88 and 131. So this whole have a MR of 147, right? Okay, let me do this over here. Where? 1 minute. There is a NH2, then CH, then CH2, CH2, CO2H, and CO2H. Okay. So here we have to do a trial and error for these masses. So if I put the masses over here, see, basically it's 14 units, it's 14 units, it's 13 unit, and hydrogen is 14 plus 2, it's 16 unit. Can anybody tell me the mass of this whole part? 2 oxygen, 32 and 12, 44, 45.
45.
And 45. Okay. So this will help me to figure out. See over here, if I have to find the structure having a mass of 88, so 147 minus 88. Yes. Can anybody tell me the answer?
Sir, 59.
59. So it means this is actually the lost. This mass is lost. So you have to figure it out. The loss of this mass.
सर ऊपर वाला जो CH2 और COH है उनको मिला के 59 बन जाता है.
C, yes, very good. This is giving you the 59. So if I remove it, this one, which means 1 minute, which means the structure which is showing the MR of 88 would be this one. ये बात क्लियर हो गई सबको? Is it clear or not?
Yes, sir.
So now this, I have again the whole structure. The total mass is 147. 131 is still there. So how much is lost?
16.
16. So this is the fraction or fragment having a 16. And these are the molecular ions. So I have to put it a positive charge. So if I remove this one, so it would be CH, sorry, CH, CH2, CH2, CO2H, and then CO2H, and then a positive charge on it. Is this clear?
Yes, sir.
Okay. Now D part at pH 11, alanine exists as this ion and glutamic acid exists as this ion. A mixture of aniline and glutamic acid at pH 11 is subject to electrophoresis. Okay. State how the mixture can be maintained at pH 11 during the electrolysis. Yes, how can we maintain the pH?
Sir, buffer, sir.
Yes, very good. Buffer solution, we always use a buffer solution to maintain the pH. Okay. So use of or using buffer. Use of buffer solution. Draw fully labeled diagram, okay, of the apparatus that would use to carry out this electrophoresis. Okay. Your diagram should include the position of the mixture of alanine and glutamic acid at the start and the start of the electrophoresis. Okay. So Okay, so what we do, you can make 2 trays like this, both having a buffer in it. Here a support, and from that support we have a filter paper that is dipped in both the tubes. Here we would place a sample. And these are the electrodes that are bonded to external, a DC supply. This is a sample. And this is paper that is dipped in the buffer on both sides. So here you have, this is your positive terminal and this is your negative terminal, or you can do it vice versa. So this is how you would make a diagram. Is this clear?
सर एक बात पूछनी है
जी
सर, इसको जिस तरह हमने इसके अंदर डाला है इलेक्ट्रोड्स के साथ उसका वो बनाया है, तो क्या हम इसको डायरेक्ट डीसी सप्लाई पे नहीं लगा सकते?
सॉरी
सर कि हम उसको सीधा डीसी सप्लाई के साथ ही लगा दें बजाय इसके कि वो इलेक्ट्रोड्स के साथ लगाओ।
you are saying that we have to connect like this?
नहीं सर, जहाँ पे सैंपल लगा हुआ है उसको सॉल्यूशन में गुजारने के बजाय सीधा डायरेक्ट सप्लाई पे लगाया हो।
Yes, the thing is that then we can't able to use a buffer solution because these solutions are the buffer solutions.
सही है सर, थैंक यू।
So we need the buffer solutions to maintain the pH. That's why we have to dip it in these buffer solutions. Is it clear?
जी सर।
सर इसमें दोनों बफर सॉल्यूशन होगा?
Yes, both the sides have a buffer solution.
ऑलराइट।
Okay. Identify the electrode that each amino acid travels towards during the electrolysis at pH 11. So if you recall alanine and glutamic acid, see, alanine is a negatively charged over here and it have actually a 2 negative charge over here, right? So both are going to going to travel towards the positive electrode. This one as well, positive electrode. Is this clear? जी यहाँ तक clear है? Is it clear to everyone?
Yes, sir.
Okay.
सर हमने दोनों पॉजिटिव इलेक्ट्रोड पे क्यों लगाए?
Yes, because
हमने
alanine have a -1 charge and acid have a -2 charge, so both are going to travel towards the positive.
Okay, चलो ठीक है sir. Thank you.
You're welcome. In a particular electrophoresis experiment at pH 11, the glutamic acid travels 3.4 centimeter, alanine travels at a short distance. Okay. Explain the factors that account for the difference in the distances traveled. So,
Sir, difference in charge and the masses.
yeah, very good. So we can say that, 1 minute. It's of 2 marks. So alanine is -1 and glutamic acid is -2. Okay. So further, we can write that alanine has lower MR. Question number
Sir,
9.
wouldn't
Yes.
alanine have, if it has lower mass, wouldn't it travel more?
But its charge is also lower.
Right, okay.
If both have a same charge and the alanine have a lower mass, then it could travel faster,
Right.
right?
Yes.
Okay. Now question number 9. Butylamine can be synthesized from different organic compounds by using suitable reagents. Each reaction involves one step. Okay. Complete the table to describe the 3 different syntheses. One of the 3 syntheses should involve a nucleophilic substitution reaction. The starting organic compound for each synthesis should contain a different functional group. A different reagent should be used for each synthesis. Okay. So what they are saying that at the end, you are getting this compound from all of the 3 syntheses, whether it's this one, or this one. You must have a 3 different functional groups, and one must include nucleophilic substitution. Okay. So if I start from the first one, it's an it's amine, not ammonia. NH3, it's NH2. So NH2 can replace halogen easily. So it means my starting material or the starting compound would be this one, or here you can put a chlorine as well. And to convert this into this, to convert the starting,
There's
yes,
3 CH2
sorry, thank you. So we have a 4, it's of a 4-1, okay, I missed it. So it is like this only. Okay, so To convert this into this one, I need ammonia. In high pressure, you can write, or you can write under sealed tube. And heating.
Sir, NH3 will be alcoholic or aqueous?
It is ethanolic. We normally use ethanolic ammonia. Next. This is an amine, and amine can be made from amide. So what would be the other organic reactant that I start with? CH3, CH2, CH2, C double bond O NH2, that is an amide. And for this amide, I would need LiAlH4 in dry ether and heat if needed. So it can convert this into this nitrile amine, and nitrile can also be, converted into amine. So I can use CH3, CH2, CH2, C triple bond N. So the same reagent can be used, LiAlH4 in dry ether.
सर उन्होंने क्वेश्चन में कहा है कि डिफरेंट रीजन्स यूज होने चाहिए हर सिंथेसिस के लिए.
Okay. So, okay. So, yeah, sorry. So in this case, we can use hydrogen in the presence of nickel as well.
Sir, can't we use NaBH4 in second reaction?
No, NaBH4 is actually basically reduces carbonyls and aldehyde and ketones, not nitriles. Okay. So NaBH4 cannot be used. Compare and explain the relative basicities of ammonia, butylamine, and phenylamine. So the most basic, if you recall, is, who can tell me which one is the most basic among these?
Sir, butylamine.
Butylamine. And then
Ammonia.
ammonia. Okay. So butylamine, ammonia, and here we have phenylamine. Okay. So the basic strength, we know that it depends upon lone pair of electrons that how readily they are available to accept H positive ions. So butylamine is strongest base as alkyl groups causes positive inductive effect making lone pair more readily available than phenylamine is the weakest base as the lone pair of nitrogen is delocalized into benzene ring. Hence not available. Is this understandable to everyone?
Sir, sir,
Yes.
सर ये जो ब्यूटाइलमाइन वाला है इसके अंदर ये लिखना जरूरी है इंडक्टिव इफेक्ट का सिर्फ यही लिख सकते हैं कि उसके अंदर जो ग्रुप है वो इलेक्ट्रॉन डोनेटिंग है तो उसकी वजह से वो लोन पेयर
Yes, you can write that as well. You can write that as well, that the alkyl groups are electron donating. So due to the induction of the electrons from them, the lone pair is more readily available.
सर ठीक है थैंक यू सर
Okay. Now, complete the table to show the structure of the organic products from each reaction of phenol. Okay. So we know that phenol, when reacts with NaOH, what would happen? This would happen, right?
Phenoxide ion.
sodium phenoxide, or you can write phenoxide ion as well. When phenol reacts with a sodium metal, again same thing happens. Like this. Then phenol with a benzene diazonium. If you recall that this is phenol over here, and here we get nitrogen double bond instead of a triple bond. This would be the structure. And an excess of phenol, which means what would happen over here? If it's an excess of phenol, then a chloride is removed from here, and one phenol, after releasing its hydrogen of an OH, bonded over here, and the other phenol removing its hydrogen and going to be bonded over here. Is this clear?
Sir, ये फिर से explain कर दें please.
Which one?
The last one.
Last one. Okay. It's a sort of polymerization, if you recall, or esterification. See, they said that excess of phenol is used. So it means, see, we have a one phenol over here, for example, and we have one phenol over here, for example. Okay. So what would happen? That from here HCl is removed, and from here HCl is removed, and then this oxygen is going to bond with this carbon, and this oxygen is going to bond with this carbon. Is it clear now?
Yes, sir. Thank you.
Okay. Now what they are saying, identify two reactions from the table in which ethanol would behave in a similar way to phenol. Okay, it means that if we have an ethanol, then ethanol would also be behaving in the same way as a phenol.
Sir, 2 and 4.
Yeah, very good. 2 and 4, because ethanol also reacts with the sodium metal, and ethanol also undergo this kind of condensation reaction. So if we have CH3OH instead of phenol, then this would happen. So you may write that 2 and 4. Is this clear to everyone?
Yes, sir.
Okay. So we have ended our paper over here, and I think, okay, we just give me a minute, please. So now we will going to start a new paper in our next class, and I will update you guys about the next class. It will be tomorrow afterwards. Okay. Okay. Take care, everyone.
Allah Hafiz, sir.
Eid Mubarak in advance.